All right. Hey everyone, and welcome back to another exciting 196 lecture. Today is a really fun one. We're going over concurrency, which is probably one of the most powerful features that Rust has to offer. So I'm just going to check. As always, if you have any questions, drop in the Twitch chat, and I'll be there to answer it as soon as possible. All right, so let's go over our objectives for today. So firstly, we're obviously going to go over concurrency. Why do we use it? Why is it so hard? And then we're going to go over threads, which is how we use concurrency in Rust and a lot of other programming languages, and how to communicate between threads with channels. So firstly, what is concurrency? So concurrency is the ability for a program to be decomposed into parts that can run independently of each other. And we have to note there's a difference between concurrency and parallelism. So in the English language, concurrency and parallelism have the same meaning. It's things happening at the same time. But in computer science, there's a slight distinction between them. So in concurrency, we have different parts of a program that execute independently, and in parallelism, different parts of a program that execute at the same time. So a good real-world example, I think, for concurrency is, take an average student, for example. You have many things to do in the day. You have to do your homework, you have to make dinner for yourself, you have to clean your apartment or your dorm. You can't do all of these things at once, but these are all distinct tasks that have to be done. So you carry out several distinct tasks, but you aren't doing them at the same time. Parallelism, on the other hand, it's very difficult for a human to do parallelism because we can't do multiple things at the same time, unfortunately. But let's think of a baker, for example. If we had a concurrent baker, what they'd be able to do is chop up food on one side, then they go over to the pot and they stir something up, and then they take whatever they're stirring and put it in the oven, like that. That's concurrent. But let's say we had several bakers who had several ovens in several parts. We could have one baker cutting while one baker is stirring something at some point, and one baker is putting stuff into the oven, and all the ovens are cooking at the same time. This is parallelism. We have multiple things happening at the same time. Thankfully, for this lecture, we don't need to worry about the distinction too much, so we're going to treat them as the same thing. We're going to label them both as concurrency. And you can see here, these diagrams are a very good way of visualizing it. If these are three separate tasks, each of these lines, and the gray bar is what is being done at this moment, and this sort of time series thing, we see we start on task 1, we go to task 2, go to task 1, go to 3, 2, 1, like that. We're only doing one thing at once, but we're working on several tasks, whereas in parallelism, we're doing all three tasks at once, like so. So why do we want to use concurrency? Computers are already so fast, why do we need to even bother, right? Well, let's take a look at 40 years of microprocessor trends. So I'm sure you're all familiar with Moore's Law, which is essentially what Moore's Law states is that every year, every 2 years, I believe now, the number of transistors that you can fit will double on a chip, will double per 2 years. What that means is your processing power is doubling every single year. And as you can see, that seems to be the trend. We have a lot more transistors, and for the most part, we are seeing faster computers every 2 years. But notice here, there's a slight drop-off with the frequency for these transistors, or microprocessors. This isn't rising at the same rate as it used to, but look at the number of logical cores. This is rising, quite a dramatic rate too. So what this means is that we want to try and utilize all these cores on our computer. Why do we want to run just a single task linearly when we have so many cores available to us? Why don't we try to split up our work so that we have multiple things happening at once? So concurrency enables us to take advantage of multiple processors in computers. Because I'm sure even the cheapest computer you can buy nowadays has multiple processors. So concurrency lets us utilize all these processors simultaneously. So this sounds great. We have amazing fast speeds, we're splitting up the work, we're more efficiently using your computer. What's the catch? Well, the issue is concurrency is pretty hard. So take a look at Firefox's code base written in C++. So this issue was reported 7 years ago. They want to parallelize the selector matching, and they still haven't done it yet. The reason? It's not because Firefox doesn't have the money or the talented developers. The issue is their code base is so large that to parallelize something like this would be incredibly difficult and would take a lot of time, a lot of testing, and their site might go down, or their service might go down. So it's very difficult even for large industry giants like Firefox. So think about for a student who's working on their MP, it's a lot to process, a lot of thinking, and you're prone to a lot of errors when you're trying to parallelize or make things concurrent. But it's really nice. Like, we really do want to use concurrency. It makes our code a lot faster. It helps us work on these huge problems that we couldn't really work on efficiently without parallelizing or making our code concurrent. And notice here, if you look at Amazon, YouTube, when they managed to parallelize their code, we could see that things took less time. The loading times decreased a lot. Parallelizing or making your code concurrent does make things a lot faster. And you can see these big tech giants, when they were doing it, things got a lot faster. So why is it so hard? It seems relatively straightforward. You have a bunch of tasks going, just split it up, make them all do it, like a bunch of little workers. So here's a motivating challenge. It's called data races. So let's take this scenario here. We have this guy here, we'll call him Jim. He is trying to withdraw $2,000. And there's a central thing here with this balance. This is the data he's trying to access. So how does this work? Well, first we want to read the balance. So obviously it's $5,000 here. Next, we're going to subtract however he wants to take. So if it's 5,000, take away 2,000, we'll have 3,000 now. And finally, we want to update the balance. Finally, we want to update the balance. So then the balance will be sent back here, and it'll say 3,000 here. But let's say, as he's doing this at the exact same time, or concurrently, his company is sending him a direct check. So at the same time, he's just read the balance of 5,000. So is his company. They both read 5,000. They both make a change. So here on the ATM side, 2,000 is removed, but here on the company side, 4,000 is added. Next, this ATM side updates the balance, that's 3,000. But then this side also updates the balance, and they've just done 5,000 plus 4,000, and it's 9,000. Oof. So this is incorrect because obviously we've withdrawn 2,000 here, added 4,000 here. The difference is 2,000. 2,000 plus 5 is 7,000. So we should be having 7,000, not 9,000. And this is what we call a data race. Because when we try to change a variable, for example, we have a variable in code called x and we want to append it, we don't just suddenly magically make it increment by 1. We have to read that value in, make a change to it, and then update that back in memory. And this case highlights that very well. And many of the challenges of concurrency, so obviously here, back to this example, when we have these errors with concurrency, it's because we're trying to read multiple things at the same time. We have multiple threads, multiple workers, all trying to access data and do things to it. We can't guarantee that we know what it's going to be if everybody's changing at the same time. But thankfully, many of the challenges of concurrency are solved by ownership. So that's that really cool thing that Sammy talked about in lecture 2. I hope you guys will remember that because it's going to be very relevant today. And ownership helps remove issues with memory safety or data races, because obviously only one person can own the data, one instance can own a data at a time, so this can help us with memory safety or data races. So what does this look like in Rust? So first things first, let's talk about threads. So threads at a high level are what we're splitting our work into. If you think about you have your linear structure of code doing something, threads are like little workers. They break off and they all run the code simultaneously so that we can solve this problem faster. So from the Rust textbook, in most current operating systems, an executed program's code is run in a process, and the operating system manages multiple processes at once. Within your program, you also can have independent parts that run simultaneously. The features that run these independent parts are called threads. Splitting the computation in your program into multiple threads can improve performance because the program does multiple tasks at the same time, but also adds complexity. Because threads can run simultaneously, there's no inherent guarantee about the order in which parts of your code on different threads will run. So this is a really key point I want to hit on. When our threads are running, we don't know how the processor on a low level is going to queue them up. We don't know which one is going to run first, which will run second. Even if we spawn a thread earlier, it doesn't mean it's going to finish quicker than a thread we spawned later, because we don't know how processing time is allocated on a low level. It could be totally random, and if we run the same code multiple times, you actually might even notice different results. So Rust attempts to mitigate the negative effects of using threads, but programming in a multi-threaded context still takes careful thought and requires a code structure that's different from that in programs running in a single thread. So we're going to teach a whole new way of programming, which you will cover a lot in later classes like 241, which is which is integral to understanding how to code for big systems. So how do we create a thread in Rust? So here's what we do, right? Thread spawn, this is the keyword, and we pass in a closure containing code we want in another thread. So if you remember from Sammy's last lecture on functional programming, a closure, is that code which you put in double bars, and it basically runs it sort of separately from like the main chunk of code that we're using. So let's go over this code here. So we spawn our thread here, and we tell the thread to run what's in this closure. So what this is doing is it's iterating 10 times, and it's printing hi, number, whatever this I is, from the spawn thread. And then at the same time, we're printing 4, 1 to 5, hi from the main thread. Something to notice here, though, is that once we spawn this thread, we just straight away jump onto this. So while this is being printed, this will also be printed at the same time. And just a note here, note the thread sleep pauses the thread. So after each iteration, just pause the thread. So what happens is we have our main thread. This is our main, our main central code here. And then we have this thread that is spawned. So once this thread is spawned, so let's say we have like a linear, like a river here. The river breaks away with our new thread that we spawned. That's doing its own thing. The main thread is doing its own thing, and they meet at the end again. So let's actually run this code snippet, because I think it's a good example. So notice here this hi, 1 from the main thread, 1 from the spawn thread, 2 from the spawn thread, 2 from the main thread, etc., 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 all the way down. But notice there's an issue here. We didn't get to 10 in the spawn thread. And the reason for that is, once the main thread finishes, so once this hits 5, the program ends. This is the main thread that's called the other thread, so once this is done, it finishes. We don't know how long the spawn thread is going to take. The spawn thread could finish well before this main thread, it could take ages, we don't know. But as soon as this main one is over, it's done. And this is an issue. What if we really needed the information from this? What if we really needed the task this was doing to be done? And again, so this is what we just had. Something to note though is the output isn't going to be the same every time. So if we run this multiple times, we could have the spawn thread running first, we could have different orders. Notice how this output here is different to the output we got when we ran it, right? And notice again that the main thread shut down before the spawned thread, this one here, reached 9. That's why we didn't get to see the rest of the output. So how can we solve the problem of the spawned thread not finishing? Save the return value in a variable. Alright, so the way we do this is we have this thing called a join. So what join does is so first we see a thread spawn returns a join handle. When we call join on it, it waits for the thread to finish. And in this case, join blocks main until the handle is done. So you see here, we're spawning this thread and we're getting this handle, and we wait here. So what happens in this code is we spawn this thread here, and we save the return value in handle. So once this is spawned, remember we have our linear stream here. We have this new spawned section on the side here. The main thread is still doing its thing, and it's probably going to finish earlier because it's printing less stuff. We don't know for sure, but it might finish earlier. If it finishes earlier, it's going to hit join. And because once we hit join, we're waiting on the return from this. So we hit join, the main thread stops moving, our spawn thread keeps moving. Once they meet up and join again, we can continue with our code. In this case, the code will just end. So now if we look at the output, we see that this time spawn finished. So we hit 5 or 4, from the main thread, and then the spawn thread just keeps going on because it has to wait on here. And I can demo that in the code itself. Let's run this. Yep, as expected, the main thread finished its thing, but instead of just stopping the whole program, we waited on the join, because the join just froze that thread for now, waited for the spawn thread to finish, and once the spawn thread finished, we could continue with the code and end the program. But another key thing to note is that where you put join matters. So we put join here initially, So what happened is this thread started and this for loop also kept going, which is why we had that mismatch of results where it said, if we go back here, we said it says, main thread did some stuff, the spawn thread did stuff, the main spawned. The reason for that is we can't control the ordering of that. The processor handles how the task is carried out, so it's totally random each time. But if we put our join up here, what happens is our thread is spawned, it's going to do its own thing, it's going to finish all its tasks, and then only once the thread returns, will we hit join, stop freezing here and continue with this. And as you can see, we have two totally different results here. We have what we saw initially, which is sort of the mix-up of main and spawn thread printing stuff, whereas here we see that only the spawn thread prints 1 to 9, and then the main thread. So actually, if we didn't spawn a thread here, we get the exact same results, because what we're doing here is sort of naive. We're spawning a thread, doing this for loop, but we're not letting the main thread run. Instead, we're halting the main thread until the other thread joins here and continues. So that stuff is a little complicated, but this is like the backbone of how concurrency works. Let me see if there's any questions for us. So coup code, I will put up the coup code in a second. What's the spawn thread return to handle? So yeah, as Sammy said, it's a join handle type. So in this case, both the threads start here. We have our main thread, we spawn a thread, this will finish, this will keep going on. Once they hit join, they can keep moving together. In our second case here, our thread is spawned, but we've already hit join on this side. On our main thread, we've hit join, so this is going to stop moving until we finish our thing, loop back, and then we can go into our main for loop here, like so. Alright, so any more questions before we jump into the Kahoot? I'll pull up the code here so you guys can access that. And of course the Kahoot music. So someone asked, if you put the join in the thread itself, would that block the thread and not the main thread? Well, if you put... See, you can't put the join in itself unless this thread is also spawning stuff. Because thread is returning to this value handle. If you put join in the closure, you're putting a variable that isn't available in the closure. The closure doesn't have ownership of that variable, so it can't actually use handle because it's returning to itself. It's sort of like a weird paradox there. So you can't do that. Someone asked, can you access variables created in the spawn? That's a great question. We're going to get to that. So that's how, when channels comes in, because obviously we might want the output from our thread, right? So we will talk about that when we're using channels. Is there a way to block the handle and let the main finish? So I don't think I fully understand that question. Do you mean, is there a way to stop the thread and let the main finish? Because that's what we did before. If we don't have this thing here, this whole chunk of code will end when the main thread ends. So even if this thread isn't finished, we'll finish there. Stop main, let the thread finish. Is there a way to stop the main, let the thread finish? I mean, yeah, that's exactly what we're doing. What the join does is join freezes the main thread and says, okay, we can move on from here until this thread has returned. So we hit this line and we say, okay, this thread is still running, so we're going to wait here until we get the return value. Once the thread returns to handle, we can join and then continue here. Someone said, sorry, I meant the opposite. Stop the thread and let main finish. Well, in that case, you do what we did here. We would... Well, no, I don't believe there's a way to stop the thread and let main finish. There's no need for that, right? If you wanted main to finish and you didn't need the value in the thread, you wouldn't call thread in the first place. You wouldn't spawn a thread. That just takes extra computation for no reason. But yeah, good questions, good questions. I'm going to give this another 10 seconds and we're going to start the Kahoot. All right, let's get started. So true or false, thread spawn with a closure is how we create a thread in Rust. All right, great job. Almost all you got it correct. This is true. This is exactly how you spawn a thread. And as you can see in our code, we use thread spawn and we pass in a closure there. You can return if you want. You don't have to do that though. As you can see in our previous example, sorry, where was that? You can just spawn it like so without returning whatever the thread is spawned. Good job. Question 2, what does thread sleep do? Gonna check for more questions. All right, great job. So unfortunately, you can't take a fat nap when you're programming. It doesn't work that way. And it doesn't stop the whole program for the time stated. What thread sleep does, it stops the thread's execution for the time stated. So if you notice here, we do thread sleep for 1 millisecond, and basically through each iteration, we let the thread sleep for a millisecond. So good job. What does join do? This is a really important part of threads. Alright, good job. I'm glad you got this correct. So join obviously doesn't delete system32. I don't know who keeps guessing the blue one. It's been consistently the off answer. It doesn't join two threads together. What join does is it blocks the main thread. It blocks the current thread and it lets us wait for all the other threads around it to finish, or the thread that we are waiting on to finish. So if I run back to this code here, when we spawn this thread, although I use the sort of the visual of a river where the thread breaks off and comes back, it doesn't join the threads. These threads aren't like one thing now. Whatever happened in this thread is totally separate to what happened in this thread. Any variables here, once they join, have gone. What the join does is join is sort of like a barrier. Once the execution of this whole thread is finished and we hit join, this main thread hits a barrier. And the only way to unlock that barrier is for our side thread to finish running, return, and then we can just move together again. So any questions about that, guys? Alright, seems good. I hope this makes sense. We are spawning threads. The threads have to do their own thing. And what they're doing is totally separate to what the main thread does. But a way that we can sort of synchronize what these threads are doing is using the join. The join blocks the main thread and waits for our returns so that once everything is returned, we can keep moving. Let's say, for example, like our thread here finishes much earlier than main. Then this won't block. This will already just return straight away and we'll keep moving and we won't waste any time there. So measures Rust takes to increase thread safety. The move keyword. So let's take a look at this here. So we've created this variable here called v. It's a vector with values 1, 2, 3. And now inside our thread, we are passing v. So this thread is saying, here's my vector v, and it's doing stuff with it. And then we have a little join there. But what if this happens? Let's say we spawn our thread here, and then we try to drop v. So dropping is what Rust automatically does. It's how it clears up memory. And it's sort of like, if you think of garbage collection, it's sort of like how Rust automatically does garbage collection. It just drops variables you aren't using anymore. Like, for example, if we call a function, once we return back to main, all those temporary variables are dropped. It's cleared from memory. But we can also manually drop, like so. So let's say we pass v into here, and while this thread is using it, we drop it. Well, what's going to happen? Well, thankfully this won't actually work. This will just crash. And the reason that this is an issue is because we don't know how long this spawned thread will take. Like, it could run much quicker than this drop v, for example. Let's say we spawn it, and by the time we hit this line, it's already done with it. But what if it takes a long time? What if the processor decides that the main is going to keep going and this thread is going to have to wait a minute? Then we'll hit drop, and we'll try to access something that has been dropped. That's an issue too. One solution could have been to move our join up here, because that way we have to wait for this to finish before we can drop it. But there's a better way. So we need to make sure v isn't used after we use it in the thread. So you remember the bank example. We can't have multiple things accessing the data and changing it, because once we come back to what we're trying to use it for, we don't know what it could be. It's not deterministic anymore. It's not deterministic. So we can use the move keyword, and this will force a closure to take ownership of the values it uses. So the way we do this is we put the move keyword before the closure, like so. And now, once we spawn the thread, v, what used to be owned by the main, is now under the ownership of the thread. So I'm going to repeat that again. Move forces the thread to take ownership of the variables here. So when v was created or initialized, it was owned by the main thread. But now, once we move into our thread here, we use the move keyword and we force the thread to be the owner of v. So now if the main thread tries to do anything to v, it'll just crash, because it doesn't have ownership anymore. And as we know from lecture 2, you need to have ownership of something to read or change a value of a variable in Rust. So now this will work, and now we wouldn't even be allowed to drop v because the main thread doesn't have ownership of it anymore. So someone asked previously, how do we pass data between threads in Rust? And it's a really great question. It's obviously something that's very, very useful. So let's cover that right now. We're going to use channels. So from the Rust textbook, one major tool Rust has for accomplishing message sending concurrency is the channel, a programming concept that Rust standard library provides implementation of. You can imagine a channel in programming as being like a channel of water, such as a stream or river. If you put something like a boat into the stream, it'll travel downstream to the end of the waterway. So just have that little visual in your head. A channel has two halves, a transmitter and a receiver. The transmitter is where you put boats into the river, and the receiver is downstream where the boat ends up. The transmitter gives the data you want to send, and another part checks the receiving end for writing messages. So in our back to our little visual that I was doing with my hands, this is the start of the river. We have a transmitter that has information and just passes downstream, down the river to the receiver who receives it. So how do we create a channel in Rust? So here is the syntax that we use for that. So typically in Rust, we use TX for transmitter and RX for receiver. And we have this thing called MPSC channel. MPSC standing for multi-producer single consumer. And we'll get into that in a second. So again, imagine multiple streams flowing together into one big river. Everything sent down any of the streams will end up in one river at the end. So let's say we have 4 threads, for example, or 4 boats, and they're all coming down this multiple streams. They all come down like this, and they all join the main river, and they just keep moving down together. Everything reaches the same receiver or the same waterway at the end. So let's take a look at this code here. First, we initialize our receiver like so, our transmitter receiver using MPSC channel. We then spawn our thread, and we give the thread ownership of the transmitter. So what we're going to do here is take this value, we're going to call it high, and this is a variable that was made in the thread. The main has no access to this value. If we try to print val down here, we'd have a crash the code would crash because this is in a totally different thread. The main thread does not have ownership of that. But what we're going to do instead is take this value and we're going to send it downstream. So the transmitter is going to take it, put it in a boat, and send it downstream to receiver. What it's actually doing is giving ownership of this value, val, and it's sending it to our receiver. So TX used to have ownership, and now RX has ownership. Our receiver has ownership of it. So we have this new value received that is taken over val. So now if we print, we get high. So let's demo that. So as always, we have this here. We have our transmitter receiver. We get this value here that is in this new thread that we spawned. Value is being passed downstream by our boat, i.e. its ownership is being given to our receiver. So now let's run it. Got high. I was going to change this to anything. Let's run that. Hi, CS196 students. So we're able to take this value, pass it downstream, so pass it from our thread that we spawned back into main, and then we can use these values. So obviously this has many purposes. Let's say we're doing multiple computations in a very large program. Why make the main thread do everything? Let's break up all the computations into different threads, pass everything into receivers, and then we can just return the final answer. This will greatly increase the speed of your code. So measures Rust takes to increase thread safety. The receiver takes ownership of data that is sent. Again, don't forget the bank example. If we had ownership in that case, only one person could change what the actual bank thinks your balance. That's what I'm looking for. Only one person, the ATM or the checking area, knows the actual value and can append the actual value. Two people can't change it at the same time. Similarly here, if val could be changed by both the thread and by the main thread here, then we're going to have a lot of issues. But since only one thing can have ownership of it at one time, it can only be changed by one thing at any given time. Therefore, we know the exact value of val at any given time. There's no non-determinism. We know exactly what it is at each given time. So let's take a look at this example here. Let's say we have our transmitter and receiver, we spawn a thread, create val, and then we send val to our receiver here. So our transmitter takes val and sends it to our receiver, passes ownership. What would happen if we were to print val here? Any guesses? Anyone in the chat want to be brave? I assume there's latency or nobody wants to talk, but that's fine. This is going to crash. The reason this crashes is because it doesn't have ownership anymore. Val doesn't have ownership of this, whatever this value is. Ownership is passed to receiver. If we try to do anything with it now, it'll crash. Ownership means only one person can own it at any given time, and this helps us keep our code safe. This will crash. So how do we take advantage of the MPSC? Because obviously if we have one thread passing values in, that's cool, but what if we want multiple threads? What if we have a really complex computation going on and we want to maximize our processor usage? We can clone the transmitter. So what does that mean? So initially we just had one transmitter here. But let's say we spawn two threads at one time and we pass the same transmitter to both. Who has ownership of the transmitter? It's an issue. So what we can do instead is use borrowing to make a copy. So we use this word clone, borrow tx here, so pass a reference of it, and we get a clone of our transmitter, sorry. What that means is that we can have multiple transmitters all sending stuff to the same receiver. MPSC, it's multiple, sorry, I forgot the acronym. Multiple producer, single consumer. We can have multiple transmitters, as our producers sending to our one consumer, our receiver. And clone lets us maximize that usage. So let's say in this example we have 2 threads here. Let's go through them one by one. We clone our thread, and then we use move to give this thread ownership of this cloned transmitter. So notice that's now in here. We now have this array of strings, so it's hi from the thread, and then we iterate over this array here, or this vector, sorry, and we send all of those values to our receiver, like so. So we're iterating over this, sending this to receiver, this receiver, this receiver, this receiver, and we're sleeping in between them. Similarly here, we have another array, or vector, sorry, of strings, more messages for you. But notice that we aren't using tx1. We're using just tx. We're not using the clone transmitter, we're using the original transmitter. Because we can't pass the same transmitter to both, because if they both spawn at the same time, we don't know who has ownership. So we have a separate transmitter here that's also sending to the same receiver. So more messages for you, we iterate over that, send those all to our receiver, and we're sleeping in between that, and then we can print what's in the receiver. And actually here we probably should have some sort of join at the end, because we don't know if they'll finish or not. But let's say there was a join. What we'll see is we'll get a sort of mismatch of what we expected to get. I assume you expected we get hi from the thread, more messages for you. But because we don't know which one starts first and the ordering, they'll just come in any random order. We can't really control that without a join. So it says hi, more from messages for the thread you. So hi from there, more from here, from there, messages there. And so et cetera, et cetera. Because these are running at the same time and they're being sent at the same time, we're not sure what the order is going to be. And if we run this multiple times, we might even get different orderings here. So before we go into the Kahoot, any more questions about how channels work, how move works, or how threads and join work? All right, if we don't have any more questions, then let's go back into our Kahoot. I'll give you guys like 10 seconds to get the code down if you haven't got it already. And I'll send this back into the chat. All right. Okay, how do we send data between threads? We just talked about this. I really enjoy the Kahoot music. It's a nice chill bop. All right, great. So most of you got this correct. The answer is transmitter. Transmitter is the boat that sends things to our receiver. So if we think of this idea of a river, it's all flowing downstream and we have the sort of bank here that everything collects to. The thing that we're sending our stuff in is the boat, which is the transmitter. Someone asked, how does Rx store the value it receives? So Rx is simply, so I should have mentioned that here actually. So notice here we aren't like iterating over it. Rx can be simply treated like an iterator. It stores things, I believe in, I don't remember exactly what it's stored in, but you can treat it as an iterator when you're using the data. You can iterate over it like you're iterating over an array or a vector. There's leaderboard. All right. The receiver borrows the values that it receives. True or false? This one's a little tricky. You have to remember your ownership stuff. Oof. All right, this was a bit of a mix, but this is a hard one. So, the receiver borrows the values that it receives is false. The reason is because it doesn't borrow the value, it takes ownership completely. We aren't passing a reference anymore. We are taking full ownership of whatever this is. So when we send it, we are taking full ownership, and now this can't use it anymore. We are just passing ownership completely to the receiver. Final question, we can only use one transmitter and one receiver with the MPSC. Just remember what the first thing an MPSC stands for, and you'll get it. Just checking for more questions. All right. Okay, so this is false. We can use multiple processors, or multiple transmitters, sorry, but only one receiver. Remember, we're thinking of it as sort of multiple streams all leading into one big river. These multiple streams are our transmitters, or we can think of it as our transmitters, and then the main river as our receiver. Remember, when we covered cloning here, we're obviously using multiple transmitters, but we only have one receiver. We can't have multiple receivers. Good job to most of you. Let's take a look at our final leaderboard just for fun. Congratulations to top 3 or top 5. To everyone, honestly, you guys did great. This is complicated stuff. All right, great job, you guys. All right, so that was everything we wanted to cover today. Next lecture we'll be going over more concurrency stuff, but using things like mutexes and other tools to make our code even safer and more robust, and how we can use it in more applications. So if you have any questions, drop in the chat right now. If you want me to go over anything again, I can do that as well. So let me know. One thing I do want to mention again, because someone asked about it, we can use our receiver like a iterator. We don't have to, if you notice in our previous example, we simply just did this whole thing here. You know, we received it, unwrapped it, and we printed it afterwards. We can just treat it like a receiver, an iterator, and just do for some value in our receiver, and then do whatever we want with that value. Like a for each loop. Someone asked, do threads in Rust take up a whole computer thread? For example, if you have a 4-thread computer, could you only concurrently run 4 threads in your Rust program? That is a great question. So it's actually a little more complicated than that, because threads first doesn't equal cores. But let's say you have multiple processes running at the same time. Even if you spawn multiple threads and you're running it concurrently, or parallel, in parallel, they don't necessarily use all the cores. Sometimes, because modern computers are very smart and very powerful, instead of running them concurrently, it'll just keep swapping between them. Like it'll have one core swapping between multiple threads continuously. So even though they're sort of happening simultaneously, it's swapping between the tasks so fast that it feels it's simultaneous, even though it's actually not simultaneous. It's like one thing happening at a time. So it sort of depends on how like the architecture is built, because modern computers don't necessarily use up, one core for each thing. They might just be one core that's swapping between multiple tasks at the same time to make it appear concurrent or parallel when it's actually sort of more concurrent. It's just in order. Good question. All right then, guys, since there doesn't look like there's any more questions, I hope that stuff made sense. If you have any more questions, obviously please ask on Piazza, drop it in Discord, and we'll get to them as soon as possible. Concurrency is a really, really powerful tool that can make code much faster and better to utilize your computer as a whole. So try to make this stuff make sense in your head. It is obviously very complicated, but once you get it, I promise you it's super useful, and you will see a huge improvement in how your code runs. So with that, I'm going to stop the stream, and I hope you guys have a great rest of your week.